this is going to be the last topic for the semester, the Net Change Theorem. So here we're going to view the second part of the fundamental theorem of calculus. We're going to consider the second part of the fundamental theorem of calculus when the integrand measures a rate of change. And the theorem states when a quantity changes, the new value equals the initial value plus the integral of the rate of change of that quantity. And that's a colon there to get us to this equation. And this equation, you can see f prime of t measures a rate of change. It's a derivative. F measures the quantity. So the old value is going to start at A. The new value is going to be represented by the time at which the new value occurs is going to be time B. The time at which the initial value occurs is going to be time A. But the new value equals the initial value plus the integral of the rate of change f prime of x across the given time interval from old to new, from A to B. And you can see that this is just the second part of the fundamental theorem of calculus with f of A moved over to the other side. But let's look at, we're going to look at three examples. The second and third are going to, we're going to have to define something else in those. But let's look at a direct interpretation of this net change theorem here. Example, a honeybee population starts with 100 bees and increases at a rate of n prime of t bees per week. Starts at 100, increases, so there's a rate of change right there, n prime of t bees per week. What does 100 plus the integral from 0 to 15 of n prime of t dt represent? Well, 100 is the initial value, n prime of t is the rate of change. So this quantity will evaluate to a new value. Which new value? Well, n measures the honeybees, the number of honeybees. Where do I write this answer? So this is from 0 to 15, time is in weeks. So we're looking at how the honeybee population is changing from week 0 to week 15. And we're starting with 100 bees. So this quantity gives the population, maybe I should just say the number of honeybees. Yeah, if I say the population of honeybees, I don't like how that sounds. I'll just say the number of honeybees after 15 weeks. 0 to 15 tells us we're looking across a time interval of length 15. Here time is measured in weeks. So this gives the number of honeybees in that population after 15 weeks. The number of honeybees in that population, that's redundant. The number of honeybees in that colony after 15 weeks would be a better way of saying it. So let's now look at, the most common rate of change we've discussed was velocity. Velocity gives a rate of change. Velocity tells us how position is changing. So here we're going to use the net change theorem to figure out a net change in position given a velocity. So here, example, a car moves due north. Remember, with velocity, we're going to have to specify a positive direction. Here, north will be our positive direction. A car moves due north at 40 miles per hour between 2 and 4 p.m. And it moves due south, maybe I should have said due south, at 30 miles per hour between 4 and 5 p.m. Okay, find the net displacement and the total distance traveled. So we're going to look for two things here. Net displacement, total distance traveled. We haven't defined total distance traveled. We'll get there. But the net displacement is going to be given by the net change theorem. Because the net change theorem tells us when a quantity changes, it tells us what the new value is. Here our quantity that's changing is position. So net displacement. Net displacement, integral from 2 to 5 of our velocity function. Velocity, let's just say v of t with respect to t. Now our velocity, notice It's defined in two different pieces. Well, okay. Before doing calculus, we can answer this question. We can answer both questions before doing calculus, without doing calculus. North, 40 miles per hour, 2 and 4 p.m. 40 miles per hour for 2 hours, 80 miles. From 4 to 5, it goes 30 miles per hour south. So from 4 to 5, it goes back down 30 miles. The net displacement is going to be this difference. You go up 80, down 30. Net displacement is 50 in the positive direction, so positive 50. Total distance traveled, up 80, down 30. 80 plus 30, 110. The next one you won't be able to do easily without calculus. But this one we can do without calculus. We're going to check that we get those answers and then see how we can interpret those answers using a graph. But how are we going to use calculus for the net displacement? The net change theorem will give us the net displacement. But notice the velocity function is defined in pieces. The velocity is 40 in the positive direction from 2 to 4 p.m. And it's 30 in the negative direction from 4 to 5. Now what do we get? Well, Fundamental Linear Calculus Part 2 gives us 40t from 2 to 4 minus 30t from 4 to 5, which gives you what? 40 times 4 minus 2 minus 30 times 5 minus 4, which gives you what? 80 minus 30, which gives you 50 in the positive direction. And that does verify what we thought the answer should be. So there's our net displacement. Now, how are we going to find total distance traveled? Well, the integral treats things below the x-axis as a negative. And the net displacement treats a negative quantity as a negative, as counting against the total value. The total distance traveled counts everything, even if it has a, even if it is given, well, it counts everything even if you're going in the negative direction. So what can we do mathematically that will treat a negative as a positive? Total distance traveled. Traveled with one L in American English. Canceled one L in American English. Total distance traveled, we're going to want what is taken as a negative by the integral to be treated as a positive, because walking backwards is still walking. And we're still going from time 2 to time 5. In both of these computations, you could have zeroed out your time at 2 o'clock and made it from 0 to 2, and then from 2 to 3. I'll stick with 2 to 5, I guess. And how are we going to do this? Well, again, our velocity function is defined in pieces. That's a 4. It's defined as 40 from 2 to 4, and it's defined as negative 30 miles per hour from 4 to 5. So we haven't taken absolute values yet, but now we can. Absolute value of 40 is 40. Absolute value of 30 or sorry, absolute value of negative 30 is 30. And here, what do you get? Well, you get 80 plus 30. Maybe I'll write that out. Fundamental theorem calculus part 2 gives you 40t from 2 to 4. Notice this would be the same if you evaluated from 0 to 2. Plus 30t from 4 to 5. And it gives you 80 plus 30, which equals 110. So in general, the total distance traveled is given by the integral of the absolute value of your velocity function. Now, before we do the next example, let's discuss a little more graphically. Let's discuss why these integrals give us what we wanted. And we're going to stick with this example because it has nice numbers. We're going to graph on the y-axis velocity. We're going to graph on the x-axis time. So to illustrate why, good job spelling why these integrals, and I'll write out the whole word. And sometimes I'm lazy and just use the integral symbol for integrals. To illustrate why these integrals give the desired quantities, consider the following. That says following. We're going to graph, consider the following graph. It might be one graph, it might be two graphs. I haven't decided yet. Let's draw it bigger. We're going to put velocity on the y-axis and time on the x-axis. Now we're going to need to go much farther in the negative direction here. From 2 to 4, there's 2, there's 4. Velocity is 40. From 4 to 5, velocity is negative 30. Yeah, that's not a function. You can break this velocity function into two continuous functions. But why do these integrals give us what we want? Well, what do these integrals measure? The integrals measure these areas, which are rectangles here. What is the area of this rectangle? Note also our units are miles and hours. Time is in hours, velocity is in miles per hour. What is the area of that top rectangle? 40 times 2. 40 miles per hour times 2 hours. Unit conversion, hours cancel, you're left with miles. So that gives you an area which can be interpreted as 80 miles. How about down here? Well, 1 hour, 30 miles per hour. Multiply them, you get an area which can be interpreted as 30 miles. So the net displacement is going to consider walking backwards as counting against your displacement. Because you're going either, well, if you're starting above, you're going closer. If you're going below, you're getting farther. But the negative is going to contribute negatively to your total displacement. Or to your net displacement, I guess I should say. So the integral of this function from 2 to 5 in this case is going to be what's positive minus what's negative. Why does the absolute value treat that lower piece as a positive? Well, it's going to take this. The absolute value, remember, just throws things above the x-axis, or, well, it flips them above if it's below and leaves them alone if it's above. And the absolute value is going to tell you that this is going to be interpreted as a positive, and it's going to contribute to the total distance traveled. So this one we could have figured out without calculus. Let's do another. Given the velocity function v of t, 3t minus 5 feet per second, find the net displacement and total distance traveled from time 0 to time 3. So the phrasing of this question, you could make it a little fancier for phrasing, like a particle travels and so on. And I'll just be direct with this. Given velocity function, find net displacement, total distance traveled. Let's do net displacement first, because that's an easier computation. Net displacement, well, integral time 0 to time 3 of our velocity function. You may be wondering in these computations for the net displacement, the statement of the net change theorem says f of b is f of a. Well, we're assuming we're starting at position 0. And we can make that assumption that we're starting at position 0. So the f of a quantity would be 0. So we get 3 halves t squared minus 5t. We're evaluating from 0 to 3. And what do we get? Well, 27 halves minus 15. Substitute t equals 0, you get 0 minus 0. So we get negative 3 halves feet. So net displacement, 3 halves in the negative direction. Total distance traveled. Well, it's integral 0 to 3, absolute value of our velocity function. Why is he erasing the first computation? There was a lot of room on the board. What's our velocity function? 3t minus 5. Now, how do we integrate an absolute value? Well, we have to break it apart into its positive pieces, break 3t minus 5 apart into its positive pieces and its negative pieces. Hopefully, it will always be positive or it will always be negative on 0 to 3. Unfortunately, this one crosses the x-axis between 0 and 3. So, where am I going to? I'm going to continue that integral computation down here, but I'm going to do some side work over here. To find, well, I'll just say we find, we find where v of t crosses the x-axis. So we need 3t minus 5. We want to set that equal to 0. You get t equals 5/3. T equals 5/3. Well, that tells us what? Well, it tells us this integral is going to split at 5/3. We haven't taken an absolute value yet. We're just figuring out, we just figured out where the absolute value changes from positive to negative, where the velocity changes from positive to negative. Now, at 5/3, it goes through the x-axis. That is between 0 and 3. Now, the absolute value stays the same. Well, the absolute value of the function is the function when it's above the x-axis. It's negative when it's below the x-axis. Well, this one is a line. So we could figure out, well, the y-intercept is down here, negative 5. So it goes like this, where 5/3 is actually over here. So on 0 to 5/3, the function is below the x-axis. On 5/3 to 3, it's above. And that would give us what? guess I'm going to write it down there. Well, that would tell us how we can evaluate the absolute value function. On 0 to 5/3, velocity is negative. The absolute value would then be its negative. I'll write it like this. Negative 3t plus 5. On 5/3 to 3, velocity is positive. The absolute value is itself. So we have, that's how it evaluates, and we can compute both of those intervals. Now, suppose you didn't know the graph of this function. Suppose all you knew, we'll go on with that computation in a moment, but suppose you just knew the function went through the x-axis at 5/3. How would you figure out which piece is above, which piece is below? Well, take an x value over here. Take x equals 1, or t equals 1. V of 1 is what? Negative 2. So that tells you on the interval 0 to 5/3, the velocity is below. And over here, is it above or below? Well, take a value inside that interval, say 2. Velocity at 2 is 1, which is above the x-axis. So that would also, that is another way you could figure out how to evaluate the absolute value. You know, look in that interval. If the inside is negative, flip it around. If the inside is positive, leave it alone. And now we have these integrals to compute. So let's compute those integrals. Equals, this is going to be a mess. I'm going to go up here. Equals negative 3/2 t squared plus 5t from what? 0 to 5/3 plus 3/2 t squared minus 5t from 5/3 to 3. So a couple power rules. Evaluate. This isn't going to fit. Okay, sorry about the board organization. The next equal sign I'm going to put over here. Equals. Substitute 5/3. 5/3 squared is 25/6. 25/9. You know, 6 is in my mind because the answer is 41/6, I think. Or maybe it's negative. No, it's positive because it's total distance and we did the absolute value. So t equals 5/3 plus 25/3. What happens when you let t equal 0? Well, you get 0. So I'll just say minus 0. Plus the other one. Substitute 3. What do you get? You get 27/2 minus 15. Subtract. What happens when you substitute 5/3? 3/2 times 5/3 squared. 25/9 minus 25/3. Then with all those numbers, you take a step back and make sure you wrote the numbers right. There are some computational shortcuts you could do in here. They're a little tedious. You know, like this number appears twice, so you could do like a 2 times something. And similarly, 25/3 shows up twice. I'm just going to go through directly. What do we get here? Well, there's where 6 shows up. I wasn't insane when I said 6. Because the 3's cancel. 3 and 3 cancel. You're left with a 3 there, so you get negative 25/6. I'm going to leave this 25/3 there, I guess. Minus 0 plus 27/2 minus 15. We already did that computation, so I'm going to combine them as negative 3/2. Minus, well, that's another 25/6 with a negative on it. plus 25 thirds. Well, more adding to do. But conveniently, 25 thirds plus 25 thirds is 50 thirds. 25 sixths plus 25 sixths is 50 sixths, which is 25 thirds. And there's a negative on there. And then that 3 halves, the negative 3 halves is still there. And what do we get? Well, 50 thirds minus 25 thirds, that's just 25 thirds. Minus 3 halves, and this does equal 41 sixths. How does it equal 41 sixths? 50 minus 9 over 6. 41 sixths feet. Or you could do the common denominator thing. So this computation, this is probably, I would consider it the heaviest computation we have this semester. But just break it down piece by piece. For the absolute value, you need where it's above, where it's below, and then you'll get something like this if you can't make a graphical observation. Make a convenient graphical observation, as may show up somewhere.